In this video, we're going to do some centripetal force practice problems. Let's start with the example we used in the last video. We've got a bucket of water being spun around so that the water stays in the bucket. Now, what are the forces we have going on here? Well, obviously, our downward force, if we just make a quick force diagram here, downward force is going to be the force of gravity. When we're at the top of our arc, that's our only force here. But when we're at the very bottom, how does that change? Well, we still have force of gravity going down, but this time the bucket needs something holding it up, something moving it around. And that force has to be the force of tension, the force of tension in that string. Now the question comes up, how does the force of tension change as that bucket spins around? At our first position here, position 1, 2, 3, and 4, at our first position here, is that force of tension higher or lower than at the fourth position? Is it higher or lower at the second position? Well, as we go up, as this bucket goes up, our tension would drop out. It would no longer be necessary because that force of gravity is pulling that bucket down. And you can try this for yourself. If you put a mass on the end of a string and spin it around in a vertical circle, you'll notice that when it's near the bottom, you can feel a stronger tug. In this last motion here, you can feel a stronger tug as it reaches the bottom of the arc, and then that tug lessens. And it doesn't really feel like it's pulling your hand up at all when it nears the top of its arc. But that's not our question. Our question here is, what's the velocity that this bucket would need to be spun at? And so we've got 10 kilograms of H2O being spun at a radius of 2.5 meters. So here we're going to have a centripetal force being equal to mass times velocity squared over r. And that centripetal force, we need an identity for that. Well, the identity for that is going to be the force of gravity. At the top of its arc, it's going to be having the force of gravity. Now we could say the force of tension, but even at the bottom of its arc, the force of tension would be equal to the force of gravity. And we don't have an equation for the force of tension. But the force of gravity is always going to be mg. And so I can say mg equals mv squared over r. Conveniently, my masses cancel out, and I'm left with the gravitation of the Earth equals v squared over r. And I have g, I always have g, it's 9.8. 9.8 equals v squared divided by my radius of 2.5. So I can take 9.8 times 2.5 and then take the square root of that. So if I want to get v, I'm going to take the square root of 9.8 times 2.5. And for that, my velocity will be 4.95 meters per second. Perfect. Let's do another one. So this problem is going to be a little bit different. In this one, I'm going to have a mass attached to a string, but this time I'm moving it in a horizontal circle. And when that mass is hanging still, it's just going to be hanging straight down. When I start to spin it, though, it starts to move away from that center of rotation until it's moving at some angle from its original position. What I want to know is, what velocity does it need to be spun at to reach an angle of 10 degrees? Now, if I increase my velocity, my angle would increase. That seems straightforward, that seems obvious. So let's start with a length of 2 meters, a mass of 0.5 kilograms, and that angle of 10 degrees. How can we solve this? Well, I've got my forces labeled here. I start with a force of tension. That's the tension of the string holding this mass. And then I've got a force of gravity that will be pulling straight down, right? That's always going to be mg. That's going to be straight down because it's going to be towards the center of the Earth. Well, the force then that I need to have moving towards that center of that circle, the center of that rotation, that would be my centripetal force. And so the identity of that centripetal force is actually going to be related to the force of gravity by a trigonometric function. And so let's define those. This is my angle right here, and so this is my opposite side, this is my adjacent side. And so I can use tangents. So tangent of theta will equal, remember, SOHCAHTOA, TOA would be opposite over adjacent. And so that's going to be my centripetal force. Let's use our colors for this. Centripetal force divided by my gravitational force. And so then we could just write that all out. Centripetal force is going to be mv squared over r. And we can make that times 1 over mg. Now our m's cancel out. Convenient as usual. And we're left with v squared over rg. And that's going to all equal tan theta. So let's rewrite that here. Tan theta equals v squared over rg. Now, we have g, that's going to be 9.8, and tan theta, we have theta, that's going to be 10 degrees. So we could simplify that into actual numbers, but we don't have our radius. So we need that radius. What is that radius going to be? Well, that is still just another triangle. That radius is going to be the distance of this red line here. And our length of this white line is going to be 2 meters. So that string's length is still 2 meters. So the radius is actually going to be adjustable for this. The radius might change based on that velocity, but it's always going to have this relationship with the length. And that's the opposite side, so we could use the sine. So it's going to be sine theta equals opposite. That's going to be our radius over hypotenuse. That's going to be our length. So let's go ahead and figure this out. So the radius is going to be equal to, let's go ahead and define that, r equals L times the sine of theta. And so now we can plug these in. So let's rearrange this top equation. Let's rearrange this so that we've got r times g times the tangent of theta equals v squared. And then let's plug in our length times the sine of theta for r. Let's put that in for that right there. So I get L g sine theta tan theta equals v squared. Now these are all known quantities, so let's go. Length is going to be 2, let's use parentheses for this, times 9.8 times sine theta, which is going to be sine of 10 times tangent of 10 equals v squared. And so let's square root this whole thing. All equal v. And so we can plug that into a calculator. And we get a velocity of 0.775 meters per second. And so that's going to be the general way that we'll solve all of these functions. And we can rearrange these equations. We can do substitution however we see fit. We can always substitute these values in. And it actually becomes very useful to be able to derive custom equations like this. Like I might want to be able to spin an object to get to any degree. And I might want to be able to go, what velocity do I need to spin at to get to these degrees? I could play around with some trig functions and I could find those values. So let's do one more. There's a carnival ride that specialized in spinning really fast with people being unsecured standing against a barrier. It would spin, 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 get faster and faster, and then all of a sudden the floor would drop out. The floor would drop away, and these people would still stick to the side. Now, this is a centripetal force ride. Most carnival rides are just playing around with forces. So what is happening here? How is this working? Well, if we want to know that, we can start by looking at the forces involved. Let's take this person right here. There's her center of mass. And then what forces are acting on her right now? Well, obviously we've got the force of gravity, right? Let's use a darker color here. Force of gravity. So we've got the force of gravity. What else? Well, what's actually holding her up? How is she actually staying up? That's a great question. Why doesn't she fall? Well, what could be resisting this motion? Well, she's pushed against that ride. So it could be force of friction. Well, if there's a force of friction, there must be a force normal. And so where would the force normal be? Well, what's the thing that's pushing her back? Her motion, the she's going to want to follow that velocity there. But this ride keeps pulling her back towards that center radius, back towards that center. And so if that ride keeps turning her, then she must have a force going inwards. She must have a force towards the middle. And that force is going to be the wall pushing against her, which is what we call a force normal. And so if we draw this out, we make a free body diagram. Let's re-identify these forces. We've got a force of gravity going down. We've got a force normal going towards the center. And we've got a force of friction. Now that force normal is unbalanced. That would be an F net. We would have an F net going towards the center. Does that make sense? Well, yeah, that should make sense. Her motion is changing. She is accelerating towards the middle. Her velocity is just keeping her moving along the outside. She never reaches the middle because her velocity keeps her far enough away. And so with that in mind, we can solve a problem like this. Let's give her a mass of, let's be nice and say 50 kilograms. And then let's say the ride has a radius of 6 meters. And let's give a mu k, let's say we want to be really safe here. Really safe and say a low mu k of 0.2. Just to make sure that we're spinning fast enough. Because if we spin too fast, that's fine. Worst case scenario, if someone loses their lunch, we kind of want that to happen anyway. But if we spin too slow, people don't stick, people fall. So we need to make sure that we consider a low friction. What's a low friction environment going to be? Okay, with all of that in mind, let's start to make some equations here. So my force of friction, that's the thing that I'm going to be looking for here. That's going to be equal to force normal times the mu k. And in this context, that force of friction has to balance out the force of gravity. So force of gravity has to equal force of friction. And so I can say that force of gravity, since force of gravity equals mg, then mg has to equal force normal times the mu k. You see how just with a little bit of free body diagramming, just a little bit of thinking about these relationships, just saying what's got to be equal, just asking where's the motion, we're able to make a custom equation here. Now we said this force normal, that's going to be our centripetal force. Fc equals mv squared over r. And so we can substitute that in as well. mg equals mv squared times mu k over r. And so our masses cancel out. That's good. That's great. That is great news. Our masses have to cancel out. Well, if our masses didn't cancel out in this problem, then that would mean that this ride would be dependent on a mass. And then you would have to say, hey, you're a little too chubby to be riding this ride. And so we don't want to have to tell our carnival goers that they can't ride the ride because they're too fat. That would not be good for carnival goers, especially considering carnival goers usually aren't that skinny. So now let's rearrange this equation. We're solving for velocity, so we're going to multiply both sides by r over mu k. And that'll cancel out r, that'll cancel out mu k. And so we get rg over mu k equals v squared, and then we can take the square root of both sides and get v. And so now let's put some numbers in for that. We've got a square root. Our radius was 6 meters times our gravitation, 9.8, divided by our mu k of 0.2 equals velocity. It makes sense that our mu k is on the bottom because the lower our mu k goes, the larger this whole number would become, right? If I divide by 0.5 versus dividing by 0.1, 0.1 would give me a larger number. And so that would mean a higher velocity. So the lower that mu k, the higher velocity. So let's plug that all in. And we get a tangential velocity, I'm going to write this over here, tangential velocity of 17.15 meters per second. So there's a few examples of how to solve problems related to centripetal force.